All right, gentle people, let's go ahead and cover section 15.6. So previously, when I was talking to you guys, I told you guys that the overall reaction does not tell you what the rate law is. And so your book gives you this example right here. They want to study this reaction. Now, what I told you guys is that if you want to go ahead and find a rate law for a particular reaction, you have to go ahead and do the experiment. So they went ahead and did this experiment in your book, and what they found out was this is the differential rate law. Now, I want you to pay attention to what they found experimentally and what the overall reaction says. Now, you'll notice that CO right here, even though it has a 1 in front of it as a stoichiometric coefficient, has a 0 order in the rate law itself. But more importantly, take a look at what happened with NO2. It is second order in NO2, and you can see that in the overall reaction, it has a stoichiometric coefficient of 1. So I hope this drives home the point that the overall reaction cannot tell you what is happening with the rate law. You have to do the experiment. But there's a deeper meaning going on here. And what that deeper meaning says is that this particular reaction doesn't proceed in a single step. And what I mean by that, it is not an NO2 molecule encountering a CO. There is a different path that this reaction is taking. So while thermodynamics was interested in the initial and final states, remember what I said about kinetics. Kinetics is all about the pathway. And so in this slide, what we're talking about is something called reaction mechanisms. And the idea behind reaction mechanisms, it is asking or trying to figure out the path that the reaction is taking place. And what do I mean by that? Well, if it's not going in a single step, that must mean that there are other little steps that the reaction is taking, meaning that there are multiple little reactions, one proceeding after the other, and that's how the reaction gets from my reactants to finally my products at the end. Now, what chemists do is they go ahead and propose mechanisms, meaning they are going to propose a series of these little steps and finally getting from reactants to products. Now, these steps that the chemist proposes are what we call elementary steps. Now, while the overall reaction cannot be written based on the stoichiometric coefficients in the reaction, the elementary step, each individual step, to be an elementary step, I can write the rate law for that particular step based on the stoichiometric coefficients, or in other terms, the molecularity of that reaction. Now, molecularity just means what things are coming together, what things have to interact for that reaction to take place. So let's go ahead and take a look at some possible elementary steps that I can invoke to try to build my overall reaction. One thing I can do is I can have my reactant just go to products. Now, if I want to talk about the molecularity of this reaction, we would call this a unimolecular process, meaning one thing reacts and then I get to my products. Now, if that's the case, I can write the rate law based on the molecularity, and that means the rate is going to be some rate constant times a to the first power. Now, if I want to invoke a step and I want to say, well, maybe A just doesn't become products, maybe A goes ahead and interacts with another A. So this is called a bimolecular process. What I'm having happen is an A molecule is going to interact or collide with another A molecule and then become products. Now, if I have this kind of elementary step where I have the 2 right in front of the A, well, then this becomes my rate law. I have to take that A and square it to show that two A's are coming. So the rate law becomes rate equals Ka squared. Now I can say, well, A doesn't need to hit another A. A can go ahead and hit molecule B, or in other words, A plus B. Again, this is a bimolecular process. Two things have to come together. And in this case, the stoichiometric coefficients 1 and 1, the molecularity 1 and 1. So that means the rate law is going to equal rate equals K, A to the first order, B to the first order as well. And they are times each other. Now, this last one I am just including for completeness sake. And that is where I have three things coming together. Now, this is a termolecular process. I'm going to let you know that a termolecular process, it is really unlikely for this to happen. What you're essentially saying is that three things have to come from three different directions, hit each other at the same instantaneous time, and then and only then they will react. What is more likely to happen is two things coming together bimolecularly, and afterwards a third thing comes together. But just to be complete, if I have these rare termolecular processes, well, I would write it based on its molecularity. Rate equals K, A times B squared, where three things are coming together. All right, so now what we see here is that our elementary steps can be written based off its molecularity or the coefficients in my reaction. So let's go see if that reaction that we talked about in the previous slide, is that an elementary step? Is my overall reaction one elementary step, or are there multiple steps occurring? All right, so here's that reaction again for you guys. And so let's hypothetically say that this reaction is proceeds in one step, and so that means the overall reaction is the elementary step. And if that's the case, what I'm saying is that an NO2 is going to combine with one CO2. So each one of these are going to collide, and what I see right here is if this were the case, the rate would equal K NO2 times the concentration of CO. Now, if I go ahead and do the experiment, and the experiment doesn't match that rate law, then I know this has to occur in more than a single step. And so we get to what is the mechanism, what steps can get me this rate law, and what is the path that this reaction is going to take. So if we understand that our overall reaction occurs in multiple steps, we have to propose the path, or we have to propose the mechanism in which this reaction takes place. Now, this is going to take some chemical intuition. Chemists spend a lot of time debating back and forth what can occur. And so you have to have a little bit of background to propose mechanisms. And what I'll do on your exams, or you can see in your book problems, is they give you a proposal and you have to verify that proposal. And so this is kind of a big idea when proposing mechanisms. And that is, you can't prove a mechanism, but you can only disprove a mechanism. And the idea here is if you throw out a proposal, you see if it matches experimental data, and if it doesn't, you've disproven that mechanism. And so you want to just propose mechanisms that are possible. So one of the things that you have to do for a valid proposal is that if you take the steps that you want to take, the path, if you add up all the elementary steps, they have to add up to the overall reaction. So here I'm going to propose a mechanism for you guys. And so what I'm going to say is that the reaction has step 1, and then followed by step 1 is going to be step 2. And so what I'm saying here is that NO2 is going to go ahead and combine with another NO2. Now this is going to generate an NO3 plus an NO. Now in the next reaction, the NO3 is going to combine with CO to make NO2 and CO2. Now there's one thing that people love to do when they propose mechanisms, and that is creating intermediates. So let's take a look at this. What we see here is in the first step, we generate this chemical compound NO3. And then in the second step, that NO3 is going to be consumed. Now, you guys can look at the overall reaction from the last slide. You'll notice that NO3 is neither a reactant nor a product. So this is what we call an intermediate. An intermediate is not a reactant or a product, but what happens is an intermediate is generated and then consumed. So it only exists in situ during the course of the reaction. Once the reaction's done, I should not have any more of that. So what we can say is that the NO3 produced and then consumed, so it goes away. Now, what you'll also notice is that this compound right here, NO2, is first consumed and then it is regenerated. Now, this NO2 right here, this is not an intermediate because it was present at the start of the reaction, and so it is a reactant, but you can see it appears on both sides of the equation, so I'm going to go ahead and cross it out. Now, if I go ahead and write this reaction now, NO2 plus CO gets me NO plus CO2. And so you guys will note that this is exactly the reaction that I was trying to study or propose a mechanism for. So I'm good so far. I have come up with some steps, and adding up those steps gets me the overall reaction, and I propose this intermediate NO3, which is produced and then consumed. All right, let's go ahead and do the next step in proposing a mechanism. So we have our elementary steps, elementary steps 1 and elementary steps 2. Now, I'm going to say that each one of these has a rate constant, K1 and K2 for each one of these reactions. And remember, these are elementary steps, so that means I can write the rate law based on its molecularity. So that means for reaction 1, the rate equals K1, and I have two NO2s coming together, so that's going to be NO2 squared. And for my second reaction, again, based on the molecularity, this is going to be K2, and in this case, NO3 times CO. Now, the question becomes, if this is my pathway, which rate law do I use, and how do I manipulate these rate laws to get the rate law for the overall reaction? Now, what you guys might have noticed is I put these descriptors on these reactions right next to the elementary step. I said one was slow and one was fast. It turns out that when you guys have elementary steps, there could be a disparity in the speed of each one of those elementary steps. I could have some elementary steps go really fast and some elementary steps that go really slow. So let's take a look at the consequence of this. So remember, the reaction is a process proceeding in 2 steps based on this proposed mechanism. So let's use an analogy. Let's say that me and my wife had this nice dinner party, and after the dinner party, my wife wanted to write nice thank you notes to every one of our guests that attended. So my wife, being a very thoughtful person, gets the card. She writes this lovely note to them saying, "Oh, thank you for coming. It's been so long to see you. It's so sorry about your parents, blah, blah, blah." She goes ahead and takes about 10 minutes to write this note. Then she hands that note to me, and I just go ahead and, because I'm a jerk, I just sign my name and just spend 2 seconds on this thank you note. Now, this whole process, step 1, my wife, step 2, me writing my name, well, this process if we wanted to measure how fast me and my wife were generating thank you notes, well, we can say, well, since my wife is taking so long versus me, the rate of our production of these thank you notes is only based on her. She is the slow step. She is the rate determining step. So if we had to crank out 6 of these notes, it would take about 60 minutes because she's taking 10 minutes each thank you note. I do it in a second. By the time that she hands it to me or she's midway through the second thank you note, I'm already done. And the same thing happens with chemical reactions. If we go ahead and have elementary steps, and one of these elementary steps is slow, that is going to determine the overall rate for that reaction. And so the slow step is going to be the rate determining step. So in our example right here, step 1, well, that was our slow step. And since it's our slow step, it's the rate determining step. And what we can see is that that means that the overall reaction is going to be based off that particular rate law, based off that molecularity of our proposal. So in this case, for this mechanism, the rate law would be this. That would be rate equals K1 NO2 squared. Now what you guys will see is that this matches what we got experimentally. So that means now I have a valid proposal. It matches the overall reaction, and now my rate law, based off of the mechanism I proposes, matches the experimental rate law. So this now is a proper mechanism. All right, so let's go ahead and try to complicate matters just a little bit. So last quarter in Chem 1B, we talked to you guys about this concept of equilibrium. Now, again, we looked at it from a thermodynamic point of view, and in a thermodynamic point of view, we cared about our initial and our final states. And more importantly, we cared about the final states in an equilibrium, where we said that once we have equilibrium established, the amount of reactants and products, they don't change concentration, and there's a ratio of products to reactants raised to their stoichiometric coefficient called the equilibrium constant. So now what we're going to do is we're going to take a look at equilibrium through a kinetic viewpoint. So that means I want to see what happens when I start, or what path am I going to take to reach equilibrium. Okay, so let's talk about equilibriums. And again, we are looking at these equilibriums through a kinetic viewpoint. So equilibrium means that my products and my reactants, their concentration are not changing. So to do this kinetically, that means the forward rate of my reaction has to equal the reverse rate of my reaction. So in these particular equilibriums, what I want you to note is that these are fast equilibriums. That means equilibrium is established relatively fast. So let's take a look at the forward rate. So I'm going to use this equilibrium up here on the top. And what I'm going to say is that this is an elementary step. And so if it's an elementary step, I can go ahead and write the rate laws based on the molecularity. So if I want to look at the forward rate, what that means is I have K1, and then I have two A's coming together. So that means that's going to be A squared. And so that's the forward rate for my reactants going to products, and in equilibrium, products go back to reactants. So then we have to talk about my reverse rate. Now the reverse rate is going to be a bimolecular process where I have B and C coming together, each raised to the first order, and then my rate constant is going to be K to the -1. Now I want you guys to note that the K's here, K and K to the -1, they have no relations. This isn't 1 over K, or this isn't K times -1 right here. These can be completely different numbers, completely different orders of magnitude. So we can write our reverse rate right here, k to the minus 1 times b times c. And let's do a little bit of manipulation right here. So what I'm going to do is I'm going to take that a squared. I'm going to go ahead and divide both sides by a squared. And then I'm going to divide both sides by k to the minus 1. And so what I get is that I get k1 over k to the minus 1, meaning the forward rate constant divided by the reverse rate constant equals bc over a squared. This might look familiar to you guys. This is products over reactants raised to the stoichiometric coefficients, or in other words, this is big K, the equilibrium constant. Sometimes you guys saw this as Kc. So what kinetics tells us is our equilibrium constant Kc can be written as the forward rate constant divided by the reverse rate constant. So with that said, we can go ahead and look at some more mechanisms. All right, so let's go to our next quiz. Here's the reaction that I want to propose to you guys. So if you're an atmospheric chemist, you guys look at ozone, O3, becoming oxygen. So what I want you guys to note is that the observed rate law, meaning the experimental rate law, was found to be this. So tell me, does this occur in a single step? So hopefully you guys came to the conclusion that this does not occur in a single step. Because if it occurred as a single step, that means I can write the rate law based on the overall reaction's molecularity. And so if I wanted to write the rate law based on the overall reaction's molecularity, that would be the rate of K times O3, and I see a 2 there, and so that is squared. Now, that's close to the experimental rate law, but you guys notice that there's something on the bottom on that rate law. So this has to occur in a multi-step process. So if this occurs in a multi-step process, let's go ahead and propose a new mechanism. And so here's my first proposal to you guys. What I'm going to say here is step 1, ozone breaks up into oxygen O2 and atomic oxygen O. That atomic oxygen is going to move on to step 2, and it is going to be combined with an ozone, and then finally I get 2 molecules of O2. So what I'm going to do is throw up a quiz. Just mark the one that says right answer. You'll get points, but what I want you to do is take a second, write what the overall reaction is, and what would the rate law be based off of this proposal. Okay, let's go see if this is a valid mechanism. So I'm going to go ahead and add my 2 elementary steps up together. Now, what you'll see in the first elementary step is I generate atomic oxygen, and in the second elementary step, I consume that atomic oxygen. So this atomic oxygen, it would be considered an intermediate. So let's go ahead and add up the rest of my elementary steps. 2O3 goes to 3O2. Now, if we take a look at this, when I add those elementary steps, they sum up to the overall reaction. So this right here matches the reaction that I was after. So I'm good having elementary steps adding up to my overall reaction. So let's see what the rate law is going to be for this proposed mechanism. So we're going to go ahead and focus on the rate determining step, and the rate determining step is going to be the slow step in my proposal. And remember, because it's an elementary step, I can write the rate law for that particular reaction based on its molecularity. And that's going to be rate equals K times O3 to the first power. Now, if I take a look at that and I say to myself, well, based on this proposal, this would be the rate law for the overall reaction. Let's see if it matches experiment. And so if we take a look at my experimental or observed rate law, that does not match. So now what I can say is this proposed mechanism is not valid. I've disproven this mechanism because it does not match what the experiment says. So let's come up with a second proposal. So here's another quiz question for you guys. I got the rate laws on the slide. I want you to go ahead and take a look at this proposed mechanism where I switched which rates were fast and which one was slow. And you guys go ahead and tell me, does this seem like a valid proposal? All right, so in this one, I was a bit of a jerk. And what you guys could have seen is that this is what you guys would have written down. But technically speaking, I did not give you a correct answer. So you should have put, I am lost. Now, the reason that choice C is not a valid answer is that if you guys take a look, inside the rate law is an intermediate. And so this is the one thing that I want you guys to remember. You cannot write a rate law based off an intermediate or have it dependent on an intermediate. And that's because an intermediate is not in the overall reaction. It is not a reactant, it is not a product. So you cannot have an intermediate inside your rate law. So how do we get around this? So let's go ahead and think about what's happening here and think about that this was a fast equilibrium. All right, so what we said is that the rate should have been K2 O3 times our intermediate O. So what does a fast equilibrium mean? A fast equilibrium means that the forward reaction equals the reverse reaction. So let's go ahead and write that down. So if I look at that first elementary step, what I would see is to go forward, I would have K1. So that means the forward rate constant times O3. And then I can have the reverse reaction. So that means I have the reverse rate constant, so K to the minus 1. And to go backwards in that elementary step, I have to have O2 combined with O. Now, what I can do is I can go ahead and rearrange this equation. What I can say is K1O3, and I'm going to divide both sides by K to the negative 1 and O2. And what that leaves me with is an expression of what the concentration of my intermediate atomic oxygen would be. So now what I can do is I can get rid of atomic oxygen in my rate law that which was answer choice C. And what I mean by that is let's do a substitution to get that intermediate out of my rate law. So if that's the case, I can write rate equals K2 O3, and then I'm going to write this expression K1 O3 K to the negative 1 O2. And so now what I'm going to do is I'm going to go ahead and just organize this a little bit more. This is K2 K1 divided by K to the negative 1. And on top, I have O3 squared. And on the bottom, I have O2. Now what I can do is I can take a look at all these constants right here. So a constant times a constant divided by a constant, well, I can combine that into one mega constant. And I'm going to call that K experimental. And that is going to be times O3 squared divided by O2. Now, if you guys take a look at this, this exactly matches the experimental rate law. I had some K times ozone squared divided by O2. So now we can say that our second proposal that is a valid proposal for what is happening in this reaction. All right, I hope that makes sense and that you guys are staying safe.